Vital Scientific Education presents a lecture in the Energy series. The topic, Equilibrium. Material in this lecture relies on an understanding of the previous lectures, energy and reactions, thermochemistry, thermodynamics and advanced concepts, acids and bases, advanced concepts, and kinetics. The kinetic lecture ended with a definition of equilibrium. A review of that material starts the lecture and is expanded into the equilibrium expression and the equilibrium constant, K. Examples of calculating K are given. Because not all reactions are at equilibrium, there is a need for the reaction quotient, Q. Perturbing conditions of a reaction alters the equilibrium. Chatliers Principle gives that some context. Finally, there's a connection made between Gibbs free energy, delta G, and the equilibrium constant, K. This is a busy set of topics, and not all students will need to explore all of the subject matter to the same degree. Know what is covered in your course. In the kinetics lecture, the reversible reaction was discussed in the context of a forward reaction, or direction, and a reverse reaction, or direction. These reactions are occurring continuously and simultaneously, as noted by the reaction arrows. The speed of a reaction is called the rate of the reaction. As an equation, the reaction rate can be expressed using either reactant or products. One form has the change, delta, of the concentration of a reactant divided by the change in time. Another form has the negative change of the concentration of the product over the change in time. The negative sign is a recognition that the concentration change of the reactants and products go in opposite directions. The first form monitors the rate of the forward reaction, and the second form the rate of the reverse reaction. Reaction rates can be built from a graph that shows the concentration of the reactant or product as the reaction proceeds. At the beginning of the reaction, there's only reactants, so the concentration of reactant is a maximum. But as time proceeds, it decreases as the reactant is consumed in the reaction. At some point, the concentration of the reactant stops changing. As for the product, its concentration starts out at 0, but begins to climb as reactants are converted to products. Again, like with reactant, at some point the concentration ceases to change. Taking this same reaction and plotting it as time versus rate has the reactants at the beginning having a large negative rate, since a maximum amount of reactant is being changed into product. This is where the loss of reactant is a maximum. The rate slowly climbs until there is no longer a concentration change. That is a rate of 0. The negative rate of the reactant continually reduces until there is no change in concentration. The rate of the product initially starts out high, since there's a maximum formation of product from a maximum amount of reactant. The rate quickly drops as the amount of reactant drops, and the change in product concentration drops. At some point, the rate levels out with a rate of 0. At some point in the reaction, the rates of both the forward and reverse reactions are 0. When the concentration of the reactant and product stop changing, the rate stops changing and are the same. A reaction is at equilibrium when the forward and reverse reaction rates are equal. They are equal when the concentrations have stopped changing. That does not mean that the concentrations are all equal. A look at the graph shows that at equilibrium, the concentration of the product is greater than the concentration of the reactant, at least for this reaction. Equilibrium does mean that the concentrations are not changing. The amount of reactant consumed in the forward reaction is matched by the amount of reactant formed in the reverse direction. Concentration not changing. The amount of product being formed in the forward reaction is matched by the amount of product consumed in the reverse reaction. Concentration not changing. The forward and reverse reactions continue, but do not produce concentration changes. Let's relook at this using a real reaction. Consider the reaction of a pair of nitrogen dioxide molecules combining to form dinitrogen tetraoxide, N2O4. This reaction can be followed visually. A test tube of all NO2 gas has a brown tinge. If it was completely converted to the clear gas N2O4, there would be no color. However, this is not what is observed. The reaction, as written, is just the forward reaction. It can also be written in the reverse direction by flipping products and reactants. The dinitrogen tetraoxide decomposes in this reaction. It is easier to follow if the two reactions combine into a single reaction using the double arrows. Written like this, the reaction is said to go in both directions. Once the reaction is started, there will always be some of the NO2 and some of the N2O4. So, what should the test tube look like? Right, a mixture. After some period of time, the color will stop changing and settle into a noticeably lighter brown tinge. This is equilibrium. When viewed graphically, the concentration of NO2 will decrease from an initially high value, and as equilibrium sets in, will stop changing. Similar type of argument is made for the N2O4. It starts out low and increases as the reaction proceeds. At equilibrium, the concentration ceases changing because the same amount of N2O4 that is being formed is breaking down. The rates also bear this out. The rate of the NO2 starts large and negative, since initially there's a maximum loss of reactant concentration, but it eases as the reactant concentration decreases. When the concentration of NO2 stops changing, so does the rate. The rate of N2O4 is initially large due to the maximum production of product, but decreases as less and less new product is being formed. When the concentration of N2O4 stops changing, the rate levels off. Equilibrium is where the rates of the forward and reverse reactions are equal. The next step in our study of equilibrium is the equilibrium expression. It was first introduced in the Acid and Bases Advanced Concepts lecture when dealing with Ka and Kb of acids and bases. The equilibrium expression follows from the logic that if concentrations are constant at equilibrium, then a ratio of concentrations is a constant. Specifically, at equilibrium, concentration of all products over the concentration of all reactants is equal to a constant value. Capital K is usually used to denote the equilibrium constant. What takes some time to become comfortable with is that it is not just one set of concentrations that produce the constant K. Any set of concentrations of reactants and products is a valid ratio if the concentrations are unchanging. That is at equilibrium, and the math comes to the correct K value. For example, if additional reactant were added to a reaction at equilibrium, the concentration of products would also go up. Eventually, equilibrium would be reestablished. The new ratio of larger concentrations would also come to that same K value. More reactants produces more products, leading to the same equilibrium ratio. The reverse is true. If product from a reaction at equilibrium were removed, the concentration of reactants would go down, since there is less product to make reactants in the reversible reaction. But once equilibrium is reestablished, the ratio of concentrations will still come to that same constant K value. The final concentrations can vary, but not the ratio. All reversible reactions at equilibrium have an equilibrium constant. Importantly, since each type of chemical reaction proceeds to its own degree of completion, every reaction will have its own K value. The ratio of concentrations is reaction specific. Also, as seen in the kinetics lecture, rates of reaction are temperature sensitive. Equilibrium constant are therefore temperature sensitive. Anytime a K value is given, it is given at a specific temperature. There are several important terms associated with equilibrium. The first set of terms has to do with the states of matter of the participants in the reaction. There are homogeneous equilibria. That is where all reactants and products in the reaction are in the same phase, all gases or all liquids. And then there is heterogeneous equilibria, in which all the reactants and products in the reaction are not in the same phase. A reaction that has a gas and a solid will have a heterogeneous equilibrium. Further defining equilibrium are terms for reaction-specific equilibrium constants. These terms only reflect the type of reaction and are not any real change to the construction of the equilibrium expression or use of the equilibrium constant. One type is called K sub Sp or KSP. It is a solubility product constant. It is used when slightly soluble salts are dissolved in a liquid. For the most part, it is associated with salts dissolving in water. Another constant is K sub P or Kp. It is the gas equilibrium constant and uses a partial pressure of the gases for concentrations. Pressure is not really a concentration, but it works for getting equilibrium constants. As was shown in the acids and bases advanced concept lecture, the Ka and Kb are the acid and base dissociation constants. See that lecture for a deeper look at Ka and Kb. A couple more points concerning the equilibrium expression. Coefficients in the balanced chemical equation have a role. For instance, this 2 says that there are 2 nitrogen dioxides on the reactant side of the equation. They can be broken out into individual NO2s. The coefficient in the balanced equation really just simplifies the expression. Writing out the 2 NO2s individually changes nothing, but it serves to demonstrate how the equilibrium expression handles coefficients. Using this revision of the equation, we can construct its equilibrium expression. No concentrations are given, so we will use the symbol of the compound to hold the place of the concentration. Begin with the concentration of the products. There's only one product compound. Write out N2O4 using concentration brackets, square brackets. That's the numerator of the ratio. The next part of the expression deals with the concentration of the reactants. Do we use one of the NO2s or both of them? The denominator of the ratio has a concentration of all the reactants. Write out NO2 in concentration brackets for the first NO2 and for the second NO2. If this reaction is at equilibrium, then the concentration of the participants are constant, and the ratio is equal to a constant. Since all the participants in this reaction are gases, we can exchange K for the more accurate Kp, gas equilibrium constant. No real change here, just a different designation for the constant. We can still clean this expression up some. Notice that the denominator has the same term twice. Something multiplied by itself is squared. This expression can also be written with the NO2 concentration term expressed as a square. The square term actually comes from the 2 coefficient in the balanced chemical equation. Both of these concentration ratios are an equilibrium expression for the reaction. Keeping the expression with the square, we can further refine the definition of the equilibrium expression as the concentration of all products raised to their coefficient over the concentration of all reactants raised to their coefficient. And like the balanced chemical equation, the number 1 is not shown. It is implied. To support this statement, consider the general reaction that has reactants capital A and B with coefficients little a and little b, forming products capital C and D with coefficients little c and d. Not a real reaction, but a handy stand-in. Writing the equilibrium expression for this reaction begins by writing out and multiplying together the concentration of all the products raised to their coefficients. The concentration of the compound capital C raised to the power of little c times the concentration of capital D raised to the power of little d. These will be over the concentration of the reactants raised to their coefficients. The concentration of capital A raised to the power of little a times the concentration of capital B raised to the power of little b. At equilibrium, this ratio comes to a constant. Bottom line, the coefficients in the balanced chemical equation become exponents in the equilibrium expression. A point or two regarding inputting concentrations into the ratio. The concentration of a pure solid or a pure liquid is 1. 100% of a pure substance is that substance. The concentration of pure gold is 1. When dealing with gases, use the partial pressure of the compound of interest. When dealing with aqueous solutions, use the molarity of the compound of interest. Let's construct some equilibrium expressions using real chemical equations. Calcium chloride dissolves in water to produce calcium ion and chloride ion. Calcium chloride is not very soluble in water. Speaking of water, sometimes it is not clear when to include water in the equilibrium equation. The rule of thumb is that if water is not included in the chemical equation, other than as an aqueous subscript, do not include water in the equilibrium expression. To get the equilibrium expression for this reaction, start by writing out the products raised to their coefficients. Calcium ion has a coefficient of 1. It is implied, not written. Also, there is a chloride ion, which has a coefficient of 2. Raise the concentration of chloride ion to the power of 2. As for the reactant, it goes in the denominator. Calcium chloride has a coefficient of 1, so does not get an exponent. At equilibrium, this ratio of concentrations is equal to a constant, K. It is temperature dependent. As mentioned earlier, some reaction types get their own particular type of K. This reaction is a salt dissolving, to some degree, in water. That degree is the solubility of the salt, and this K is referred to as the KSP, the solubility product constant. Again, no real change in what K is, only in what K is called. One more point here. When dealing with pure solids or liquids, the concentration is 1. Calcium chloride is a pure substance and will have a concentration of 1. Mathematically, we can ignore the multiplication or division by 1. It is a common practice in setting up equilibrium expressions to ignore compounds with a concentration of 1. This solubility equilibrium expression simplifies to just the concentration of the ions. Is including the calcium chloride wrong? No, it isn't. The math is the same. Still, this version is easier to follow and easier to use in further calculations. A second example is the base dissociation of ammonia in water, producing hydroxide ion and the conjugate acid ammonium. The numerator of the equilibrium expression has the concentration of the product hydroxide ion times the concentration of the product ammonium ion over the concentration of the reactant ammonia. Since all the coefficients in the chemical equation are implied ones, there will be no added exponents. Again, we will see that even though the reaction takes place in water, the concentration of water is not included in the expression. At equilibrium, the ratio gives a constant value. This reaction is a base dissociation reaction, and a more appropriate K is Kb. Now we're ready to further explore the equilibrium constant. As previously stated, they are temperature dependent. A K will always have a temperature associated with it. Equilibrium constants do not have units. They are just numbers. The real power of the equilibrium constant is that they show which direction the reaction favors, the forward or reverse direction. If K is much larger than 1, a very large number, then the forward reaction is favored. There are more products than reactants. For the equilibrium expression to generate a really large number, the numerator has to be larger than the denominator. Conversely, if K is much less than 1, a very small number, then the reverse reaction is favored. There are more reactants than products. For the equilibrium expression to generate a very small number, the denominator has to be larger than the numerator. Another feature of the equilibrium constant has to do with how a reaction is written. The equilibrium constant written in the forward direction is the reciprocal of the equilibrium constant when the reaction is written in the reverse direction. This is better shown than claimed. Take this generic reversible reaction as written. The equilibrium expression generates a K. For demonstration purposes, we will say that the reaction is written in the forward direction, and the K is called K forward. Moving this relationship to the side, we will now look at the reaction as if it was written in the reverse direction. C and D are now reactants, and A and B are products. This is an absolutely valid way to write a reversible reaction. The equilibrium expression for the reverse reaction has the new products, A and B, in the numerator, and the new reactants, C and D, in the denominator. Its equilibrium constant can be called K reverse. Both K forward and reverse are dealing with the same reaction, but when the reaction is written in one direction versus the other, the ratios are reciprocals of each other. That is, flip one over and get the other one. If the ratios are reciprocals, then so are the equilibrium constants. If we were given an equilibrium constant for a reaction written in one direction, then we can find the equilibrium constant for the reaction written in the other direction by taking 1 and dividing it by the given equilibrium constant. Some calculators even have a button, 1 over x, that does it for us. As an example, if the equilibrium constant for a reaction written in the forward direction is 1.7 times 10 to the 7th, then the equilibrium constant for that reaction written in the reverse direction is 1 over 1.7 times 10 to the 7th. My calculator gives that value to be 5.9 times 10 to the minus 8th. A way to make sure the math is done correctly is to multiply K forward by K reverse. Being reciprocals, they should multiply to 1. A logical follow-up question might be, how do we get an equilibrium constant? There are 2 ways to determine an equilibrium constant. The best way is to look it up in a table. Most chemistry textbooks have several tables of common reactions with their Ks, usually at 25 degrees Celsius, listed in the appendix. Here's a table of acid dissociation constants, Ka. It also includes pKa's. If getting pKs is a topic covered in your class, go check out the Acid and Bases Advanced Concept lecture for doing that log math. Here's a reaction-specific table. These are experimentally determined values and have a temperature dependence. The other way to calculate the equilibrium constant is by using the equilibrium expression and the given concentration values. It's not as bad as it seems, and we'll do a couple calculations to back that statement up. Take the reaction of silver ion with aqueous ammonia, forming the complex ion diamine silver. All species in the reaction are aqueous. And to determine a K for this reaction, the concentration of each must be given, and they should be given in molarity. Here are the molar concentrations for the reactants and products of one reaction. These represent measured values, which is why they must be given or determined. To get a K, construct the equilibrium expression. Concentration of all products raised to their coefficients over the concentration of our reactants raised to their coefficients. Note that the ammonia is raised to a power of 2, as expected from its coefficient of 2 in the chemical equation. To get the K, input the given concentrations into their appropriate place in the expression, starting with the numerator. The concentration of diamine silver is given as 5.0 times 10 to the minus 4th molar. Units are not included inside the concentration brackets. Just put the number. As for the denominator, the concentration of the silver ion is 3.0 times 10 to the minus 11th molar, and the concentration of the ammonia is 1.0 molar squared. Taking out our calculator and inputting values should yield a K of 1.7 times 10 to the 7th. That's quite a big number. And it means that the forward reaction is favored, with the products having a larger concentration. One more example, the Haber reaction. Nitrogen and hydrogen combine to form ammonia. Since these are all gases, the concentration of the species in the reaction is given in partial pressure. Begin with an equilibrium expression. Concentration of products raised to their coefficients over the concentration of our reactants raised to their coefficients. Concentration of ammonia and hydrogen are both raised to their respective coefficients. There is one more change in form that we should do before proceeding. Since the concentrations of the participants in the reaction are in partial pressure, the square brackets of the concentrations need to be replaced by parentheses and a capital P to indicate pressure. This is a convention and a recognition that pressure is not technically a concentration. Still, this is a valid equilibrium expression. The partial pressure of ammonia raised to the second power over the partial pressure of nitrogen, and the partial pressure of hydrogen raised to the third power. And given that this homogeneous equilibrium contains only gases, the K is more appropriately called Kp, the gas equilibrium constant. To calculate Kp, input the concentration of the product ammonia, 0.166 atmospheres squared. Do not include units. Over the reactants, starting with nitrogen, 2.46 atmospheres, and then hydrogen, 7.38 atmospheres raised to the third power. This calculation has many places to do math errors. A safe way to proceed is to do the separate calculations on the concentrations raised to a power, and then do the ratio. A final answer has the Kp as 2.79 times 10 to the minus 5. That is quite a small number, and it means that the reverse reaction is favored with the reactants having the larger concentration. A more advanced concept with an equilibrium expression and constant is finding a concentration. Many students will not be asked to do this, but for those that will, the topic is covered here. When given a K and all the concentrations of all but one species in the reaction, the unknown concentration can be solved for by algebraically isolating the unknown in the equilibrium expression and inputting the known concentrations and the K in the solved expression. What would that look like? Bringing back the formation of the complex ion diamine silver and saying that we have been provided the K and concentrations for the reactants at equilibrium, we can solve for the concentration of the product at equilibrium using the equilibrium expression and the given values. Essentially, this is an algebra problem where the object is to isolate the unknown on one side of the equation and add known values to the other side. How do we isolate the diamine silver? Well, it is in a fraction, so why not multiply both sides of the equation by the denominator of the fraction? This way, on the left-hand side of the equation, the concentration of silver ion cancels out, as does the concentration of the ammonia squared. The concentration of diamine silver is equal to this expression. K, the concentration of silver ion, and the concentration of ammonia squared. Insert known values and solve. That is K, 1.7 times 10 to the 7th, times 3.0 times 10 to the minus 11, times 1.0 squared. 1.0 squared is 1. The concentration of diamine silver is 5.0 times 10 to the minus 4. Algebra. We've made a number of equilibrium expressions based on the ratio from this definition, but we have not explored the ratio of concentrations when the reaction is not at equilibrium. This is an important distinction. If the reaction is at equilibrium, then the ratio of concentrations equals the constant K. But if the reaction is not at equilibrium, then the ratio of concentrations is said to equal Q. The letter Q is called the reaction quotient, as in division. It is used to represent the expression when the concentrations are not constant or have been pushed out of equilibrium. As stated before, a reaction is at equilibrium when the forward and reverse reaction rates are equal. So Q is used when the rates are not equal. The strength of Q is that in comparison with the equilibrium constant K, it can tell whether the forward reaction rate is currently greater or the reverse reaction rate is currently greater. In other words, it is an indicator of how the reaction proceeds to get back to equilibrium. Specifically, if Q is larger than K, then there are too many products compared to reactants. Treating the expression as a fraction, Q is larger than K when the numerator is proportionally larger than it is at equilibrium. To get the reaction back to equilibrium, the reverse direction proceeds at a faster pace than the forward direction. More product needs to be consumed to get the proportion back down to where it belongs. When that happens, the concentrations will again combine to give the value of K. If, however, Q is less than K, then there are too many reactants compared to products. Q is less than K when the expression has a denominator that is proportionally larger than it is at equilibrium. This happens early on in a reaction when there's still a lot of reactant. The pace of the forward reaction is greater than the pace of the reverse reaction. As the concentration of reactants decreases, the ratio approaches the equilibrium constant. Let's see how this works using a now familiar reaction, formation of diamine silver, and a couple set of concentrations when the reaction is not at equilibrium. The equilibrium expression is written out with Q instead of K because we believe the reaction is not at equilibrium. If the concentrations from our previous encounter with diamine silver were used, the expression yields a value of 1.7 times 10 to the 7th. That is K, and Q can legitimately be replaced by K. That value will be kept as a new set of concentrations are added. Is this reaction at equilibrium? Well, just looking at the concentrations is not going to tell us. We need to do the math. This set of concentrations gives a Q of 5.6 times 10 to the 2nd. Comparing this value to K shows Q to be smaller than K. If Q is less than K, there are too many reactants compared to products. The forward reaction moves at a larger rate as reactants are turned into products. One more set of concentrations. And again, we cannot tell if the reaction is at equilibrium just from looking at the numbers. Doing the math has Q at 8.8 times 10 to the 8th. Compared to K, Q is bigger at this point in the reaction. If Q is bigger than K, then there are too many products as compared to reactants. Why are there too many products? We don't know. Maybe the reaction started out with some diamine silver already in it. What we do know is that the reverse reaction rate will have a faster rate. The concentration of reactants will have to increase before the reaction reaches equilibrium. This reasoning out how the reaction should proceed to get equilibrium is a form of Le Chatelier's principle. When a chemical equilibrium is disturbed by a change in conditions, the equilibrium shifts to oppose the change. What causes the change is not the focus. How the system responds to the change is. Le Chatelier's principle is a recognition that equilibrium is a balance of the rates of the forward and reverse reactions. If a change in condition provides one of the reaction rates an advantage, it becomes favored. The faster rate works to remove or use up the advantage. 3 types of disturbances are covered here, along with the logic of how the reaction reestablishes equilibrium. The first disturbance is the one we just covered, a change in concentration. All 3 disturbances will use the logic of change in concentration to explain the reestablishing of equilibrium. When concentration is changed, the equilibrium constant becomes the reaction quotient Q, and neither the forward or reverse reaction rate becomes favored. Using the generic equation as an example equation, if the concentration of one of the reactants goes down, then the reverse reaction rate becomes greater than the forward reaction rate. The shift in rates causes more reactants to be produced. The change is opposed. If the concentration of one of the reactants goes up, then the forward reaction rate becomes greater than the reverse reaction rate. There is a shift to consume more of the reactant. The same logic can be applied to the other reactant and the products. Oppose the change. The second type of disturbance is a change in the pressure or volume. Ultimately, these types of changes can result in a change in concentration. Add more water to a reaction, and the molarity of the dissolved species will change. Change the total pressure, and the partial pressure of the gaseous species will change. The logic of how the equilibrium reestablishes itself is the same as argued with the first type, change in concentration. The equilibrium shifts to oppose that change. We ask ourselves how the concentrations need to change to get the ratio back to K. That follows the same thought process that we used in the introduction to the reaction quotient. A topic of disturbance not discussed so far in this lecture is a change in the temperature of the system, producing or consuming heat. A reaction that produces heat is exothermic. Since heat is a product of that reaction, it can be added to the chemical formula. No, this is not commonly done, but it is an accurate portrayal of the reaction. It allows us to treat heat like any other component in the reaction and reason the shift in reaction rates to the addition or removal of heat as a disturbance. For example, if heat were added to the reaction and the temperature of the reaction goes up, Le Chatelier's principle argues that the equilibrium will shift to oppose that change. How is added heat opposed? By opposing the formation of heat. Adding heat to an exothermic reaction is like increasing the concentration of a product, which pushes the reverse reaction. And if heat is removed from an exothermic reaction, That is like removing the concentration of a product, which pushes the forward direction of the reaction to make more product in order to reestablish the equilibrium. That is a change in temperature of an exothermic reaction. What if the reaction is endothermic? These reactions consume heat. As such, heat can be treated as a reactant in the reaction, and increasing or decreasing the temperature will be thought of as changing the concentration of a reactant. If heat is added to the system and the temperature goes up, it is like increasing the concentration of a reactant. More reactant pushes the forward reaction rate to consume more reactant and produce more product. Removing heat and decreasing the temperature is like decreasing the concentration of a reactant. That has the effect of promoting the reverse reaction. Products are used up to make more reactant and more heat. The Chatliers Principle follows the logic of making less into more and more into less. The final topic of the lecture is relating equilibrium to energy. Equilibrium is really just a different way to look at the energy of a reaction. The energy of interest is Gibbs free energy, G. From the previous lecture, we saw that G is a measure of the chemical energy. The change in the chemical energy of a reaction is the change in enthalpy, delta H, minus temperature times the change in entropy, delta S. At equilibrium, the free energy of a reaction is related to the equilibrium constant, K. The formula for the relationship is delta G equals negative RT times the natural log of K. R is the familiar gas constant, T is temperature in Kelvin, and Ln stands for the natural log. Most calculators have a button for that. This formula is a bridge between energy and equilibrium. It can be algebraically rearranged to solve for K. Equilibrium and energy are two different ways of looking at the same reaction. The energy of the reaction can be used to calculate the equilibrium constant. The equilibrium constant of the reaction can be used to calculate the energy of the reaction. Either way, the employment of these formulas is generally safe for more advanced chemistry courses. And that concludes the material of the lecture. As a recap of a very advanced lecture, a reversible reaction is where products can react to reform reactants. Equilibrium follows from kinetics. At equilibrium, the forward and reverse reaction rates are equal. It is not that they stop, it is that there is a match of consumption and production. If concentrations are a constant at equilibrium, then a ratio of concentrations is a constant. That is designated K. An equilibrium expression is generated from the reaction by placing the concentration of all products, raised to their coefficients, over the concentration of all reactants, raised to their coefficients. Equilibrium constants do not have units. They are temperature dependent. A K is given at a particular temperature. K is a powerful source of information. If K is a lot larger than 1, it means that the forward reaction rate is favored. More products are made. If K is a lot smaller than 1, it means that the reverse reaction is favored. There'll be more reactants around. There are reaction-specific equilibrium constants. KSP is a solubility product constant. It is used for slightly soluble salts. Kp is the gas equilibrium constant. All species of the reactions must be gases. Partial pressure is used for concentration. The equilibrium constant for the reaction written in the forward direction is the inverse or reciprocal of the equilibrium constant for the reaction written in the reverse direction. An equilibrium constant can either be looked up or calculated from concentrations in the equilibrium expression. The equilibrium expression equals K if the reaction is at equilibrium, but not all reactions are at equilibrium. The equilibrium expression equals Q if a reaction is not at equilibrium. Q is the reaction quotient, and brings its own kind of information. If Q is larger than K, then there are too many products, compared to reactants, for the reaction to be at equilibrium. The reverse reaction rate will be stronger than the forward reaction rate. If Q is smaller than K, then there are too many reactants. The forward reaction rate will have the upper hand. This logic is summed up in Chatliers Principle. When a chemical equilibrium is disturbed by a change in conditions, the equilibrium shifts to oppose that change. Changes include changing concentrations, changes in the pressure or volume that leads to change in molarity and partial pressure, and change in the temperature of the system. How the reaction responds is dependent on whether the reaction is exo or endothermic. At equilibrium, the free energy, delta G of a reaction, is related to the equilibrium constant. And that concludes the lecture. The last formula shows that kinetic and equilibrium are connected by energy.